Hey y'all, welcome to lesson 47, structure 2.2.9. So we're going to go over, given comparable molar mass, the relative strengths of intermolecular forces, and that generally goes with London dispersion being the weakest, followed by dipole-dipole, with hydrogen bonding being the strongest. We'll also explain the physical properties of covalent substances, including volatility, electrical conductivity, and solubility in terms of their structure, which will once again directly relate to intermolecular forces. So with that out of the way, let's actually talk about what changes the strength of an intermolecular force and what that affects. So we learned in our previous lesson that phase changes with molecules, so our covalent structures, are dependent on these intermolecular forces, on IMFs. So to go from like a liquid to a gas, we must overcome IMFs, because those are what's holding these molecules together. So if we have a bunch of little water molecules in a beaker, to actually get one of these to leave, we need to break the hydrogen bonds between our water. So IMS will actually determine how easy it is to boil something. And that's generally what we use to look at the strength of the intermolecular forces, the boiling point. Therefore, also, a stronger IMF would mean it's harder to boil, or it takes more energy, which is the same thing as saying a higher temp. So when we have a very strong IMF, it takes a lot of energy to boil that. And there's a couple things that affect the strength of the force. So there are two factors that affect IMF strength. We're going to go over both of them in detail, but those two factors are the type of IMF. Oops, that M looks terrible. And the size of molecule. So those are our two main factors that will affect the overall strength. So without further ado, let's go into the first one, type. So we have our four IMF types, which actually kind of come down into three types of IMFs. We have H bonds, dipole-dipole, and LDFs. I know we have dipole-induced dipole, but we don't really have to worry about that right now because what we're looking at is individual substances, so things that are only one molecule. So they'll all be of the same actual type of molecule, meaning they'll either all exhibit H bonds, all dipole-dipole, or all LDF. Well, to be fair, LDF appears in any of these as well because all molecules have electrons that therefore will work with LDF. So when we're looking at our three types of bonds here of only one substance, what we can do is take a look at the graph of the boiling points of these. So let's take this graph. It's a little hard on this black background. Let me just pause for a minute. We're going to light mode for a bit, so sorry for that bright color switch, but we need to see this graph, and we'll be right back in dark mode in just a minute. So we can notice a couple things right off the bat. We notice that right here at the bottom, these are all going to be, for records, H, H some value Y, so some type of hydride. So the only thing that actually matters is going to be what we're bonding it to. So right here at the bottom, we have these in group 14, which all kind of have the structure of this. And you'll notice that all of these are symmetric, so all of these are nonpolar. And now C could be replaced just as easily with silicon, or could be replaced just as easily with germanium, or could be replaced just as easily with tin. And it's all going to be the same structure, which means they're all going to be nonpolar. And you'll notice that they are at the bottom of the graph, meaning that they have the lowest boiling point and therefore lowest boiling point, which therefore means weakest IMF. And because they're all nonpolar, we know that that IMF is London dispersion forces because they are all nonpolar. So we note that London dispersion forces are the weakest. Then we move up and we see this new group right here. I'm going to exclude the ones to the left for a moment. These all exhibit, these are all polar, and they all exhibit dipole-dipole. Now we know they're not hydrogen bonding because they're not bonded to, they're not bonded to oxygen, fluorine, or nitrogen. So they're all dipole-dipole. And because they have a higher temperature, we know that these are also going to be stronger than LDF because they have a higher boiling point. So just from boiling point alone, we can see that LDF is the weakest, followed by dipole-dipole. And then we notice that for each of their periods, we have this category over here. These are all going to be our H bonds. So these are all hydrogen bonding. These are all very polar, of course. And you'll notice they have a much higher boiling point than the molecule next to them. Now, sometimes the molecules get a little higher overall, like antimony is a little bit above nitrogen, but that's all right. In general, these H bonds have the highest boiling point, and therefore the strongest IMF. So just by looking at boiling point of these hydride compounds, we can see that the highest boiling point comes from H bonds, meaning it's strongest, followed by dipole-dipole, followed by London dispersion. So our ranking of strength goes H bond, stronger than dipole, dipole, stronger than LDF. Now, above all of that, just to keep in mind, is always our intramolecular, because when we boil, we're not actually breaking the compound, so these are going to be our covalent bonds, which also, going back to a previous unit, is why things like diamond have such high boiling point. They don't even have intermolecular forces, except for London dispersion, of course. They're just all covalent network structures, and therefore all have intramolecular forces holding them together. So, with that said, this is why we see that hydrogen bonding, then dipole, then LDF in terms of strength. All right, we are going to switch back to dark mode. Oh, it wasn't that. There we go. So, moving on to point 2, size of molecule. So you'll notice back in this chart that we can maybe see a little better now, that we always increase in boiling point with the exception of the hydrogen bonds. So why does the bonding increase? Well, let's specifically look at these group 14 halides. So let's observe our hydrides, group 14 hydrides. So we notice that they are, of course, all nonpolar, and the only thing changing is the central atom. It goes from carbon to silicon to germanium to tin, and yet it increases pretty consistently. So what's changing? Well, the molecule is getting bigger. And as it gets bigger, we also get a higher boiling point. And we also can tell that there's only London dispersion forces, which tells us that London dispersion forces increase in strength when molecules get larger. LDF increases strength as molecules increase in size. Now, the important thing here is as they increase in size, what we really mean is more electrons. Because once again, London dispersion forces are based on the movement of electrons. Something to note is that a large size means more electrons, which means more asymmetry in electron distribution. Therefore, this whole thing means that they are more susceptible to induced dipoles. And they'll get even stronger induced dipoles because they have more electrons. So it's kind of this flow chart where we want this really large size, and that's going to give us stronger dipoles overall. So those are the two factors, the size of the molecule and the type of intermolecular force. All right, so moving on, let's go over properties. We have to cover a few of them. We already know boiling point and melting point as we use that as our main descriptor. But let's look at a couple new ones. Let's look at first electrical conductivity, and this is a fast one. So we already learned that electrical conductivity, we need moving charged particles. Well, in IMFs, we have no charges. We specifically have no charges in molecules. That's kind of the whole point of them. They're not charged. We only have partial charges. So if we have no charges in molecules, therefore, we have no electrical conductivity. So this is a pretty easy one. We just don't have it. If you look at things like sugar or diamond or regular coal, we're not going to have electrical conductivity. If we look at things like rocks of sulfur, again, no conductivity. We only get in really niche cases like graphite or graphene, where we get these superstructures that have these electrons that are delocalized. So mostly we have no electrical conductivity. All right, so let's move over to our next property, which we've already discussed in a previous lesson, but it's volatility. Volatility, we've said, is the tendency to become a gas, but we're going to be a little more specific. It's tendency for a molecule or an atom or whatever to vaporize via evaporation. We've also discussed the difference between evaporation and boiling. Evaporation is only at the surface. So we know that boiling point decreases with low IMF. Therefore, it's more likely to vaporize if those forces are weaker. So weak IMFs mean it's easy to vaporize. Therefore, weak IMFs also means a high volatility. So anything that you can like smell, like perfumes or gasoline, those have very high volatilities. They are very likely to break apart from their substance. When we have a container of them, it's very likely that we can just get molecules to fly out at room temperature and pressure, and they will just kind of move into the atmosphere because those forces are very weak. Weak forces. So anything that's pretty much a gas at room temperature, like butane, is going to have very low volatility, or sorry, very high volatility, very low intermolecular forces. So that's volatility. Now we have solubility. Solubility, we're going to talk about it a little differently than we have before. We're going to look at substances of same and different intermolecular forces. So when we look at a solvent, a substance will dissolve in, whoops, in a solvent if they have similar IMFs. So what I mean is when we look at water and oil, they don't dissolve because water is polar, oil is nonpolar. We generally use the term like dissolves like. And what that means is polar dissolves polar and nonpolar dissolves nonpolar. So this is really interesting because then we can start seeing almost a discrepancy in solubility as the forces change. Because we also have some substances with varying polarity. So this is kind of a weird situation where we're going to start seeing it more and more as we go into organic chemistry. But if we look at something like ethanol versus hexanol or hexane 1-ol. So ethanol is just, oops, not an E, it's just two carbons with an OH, an alcohol group, or hydroxide, depending on what you're learning at the moment. And hexanol, hex meaning six, is the same thing, but with six carbons. And now I'm having trouble counting my carbons. And so we can notice a couple things about this. And one thing you'll notice is I'm only drawing skeletal structures. I have not put the electrons around the oxygen, and that's all right, because right now I'm kind of drawing an organic diagram. And generally in organic chemistry, we don't bother with the lone pairs. We just kind of know they're there if they are. But anyways, we know this is very polar. These are spots of hydrogen bonding, and I'm actually going to highlight that on both. So this and this are very polar. But we also notice that we have this kind of big back end. And that kind of looks pretty non-polar. And so even though both of these molecules are overall polar, they're going to behave differently in a polar and non-polar substance. In something like water, oh, in water, ethanol dissolves better because it's more overwhelmingly polar than hexanol. And something like a nonpolar solute like oil and something nonpolar like maybe just hexane. So just that whole thing but minus COH. Hexanol dissolves better. So we get this varying solubility based on the intermolecular forces present. So it's going to be something that we're going to consider a lot more in the future, but as we move into our next topic, chromatography, which will be the next video after this, it will become also vastly important to understand not just polarity, but kind of the degrees of polarity of an individual molecule. So I hope this helps and have a great day.